In the middle of a Norwegian winter, with temperatures below -30 degrees, a wooden building from the year 1180 held its interior at 46 degrees. Without heat, without insulation, and without power. Today, a modern home can freeze solid in less than 12 hours. So the question isn't how advanced our buildings are, it's why we forgot how to make them survive. Soja. In the winter of 1872, Norway was locked in one of the coldest seasons anyone could remember. Snow piled up in thick drifts across mountain valleys. Winds tore through forests with enough force to rip canvas and splinter exposed wood. Outside the Borgenstave church, temperatures plunged to -31 degrees Fahrenheit, cold enough to kill unprotected livestock in hours. And yet, inside the church, the air remained calm. Still, survivable. This structure had been standing since the year 1180. There was no furnace, no insulation, no glass sealed with argon, no fire burning anywhere inside. Still, the temperature held steady at around 46 degrees Fahrenheit. Cold, yes, but stable. Livable, predictable. By modern standards, this should be impossible. Today, cut power to a typical American single-family home when it's 14 degrees outside, and the result is catastrophic. Within 6 hours, indoor temperatures fall below freezing. Within 12, pipes burst. Within 24, the house becomes structurally and biologically hostile to human life. Yet here was a wooden building, nearly 7 centuries older than the Industrial Revolution, quietly ignoring the laws modern construction claims to obey. The obvious question isn't how impressive this is. The question is, what did builders back then understand that we no longer do? To answer that, you have to stop thinking about buildings as machines and start thinking about them as physical systems. Long before thermostats and utility grids, people in Scandinavia built for one enemy above all others: winter that did not forgive mistakes. Between the 13th and 17th centuries, thousands of log structures were built across Norway, Sweden, and Finland. Cabins, churches, farms, and storage buildings rose in landscapes where temperatures could remain below freezing for months. Many of these buildings are still standing today. They didn't survive because they were lucky. They survived because they were designed around 3 physical principles that modern construction largely ignores: thermal mass, airtightness, and heat storage. Not individually, as a system. Modern buildings treat heat as something to be constantly replaced. Lose heat, burn more fuel. Run the furnace harder. Push warm air faster. Ancient builders did the opposite. They assumed heat would eventually disappear and designed buildings that slowed time itself. That difference matters more than insulation labels or energy ratings. To see this clearly, we have to jump forward, not backward, to the year 2010. At the Norwegian University of Science and Technology, researchers decided to test a question most engineers assumed was already settled. They built 2 small houses, each about 430 square feet, and placed them side by side in the same cold valley. One house followed modern standards: vapor barriers, high-performance insulation, triple glazed windows, an R value of 25. On paper, it was energy efficient by every accepted metric. The other house ignored everything modern codes recommend. It was built as a medieval log cabin, solid logs 12 inches thick, joined by hand using traditional scribe-fit techniques. No insulation, no vapor barrier, no modern materials at all. Both buildings were heated to 68 degrees Fahrenheit. Then, the researchers shut the power off. What happened next should make anyone involved in modern construction deeply uncomfortable. Within 9 hours, the modern house collapsed to 36 degrees. Cold enough to cause hypothermia. Cold enough to destroy plumbing. Cold enough to force evacuation. The medieval cabin didn't flinch. After 48 hours without heat, it was still 54 degrees inside. After 72 hours, 3 full days, the temperature remained above freezing, at 43 degrees Fahrenheit. The modern house was uninhabitable. The medieval one was still survivable. This wasn't a fluke. It wasn't an anomaly. It was physics doing exactly what physics always does. The problem wasn't that modern insulation failed. The problem was that insulation was never the full story. Modern engineering relies heavily on R-value, a measure of resistance to heat flow under steady conditions. Higher R-value, better insulation. Simple, clean, easy to market. But R-value ignores something critical: thermal mass. A 12-inch thick wall made from old-growth pine weighs roughly 80 pounds per linear foot. That mass can absorb, store, and slowly release enormous amounts of energy. When heat enters the building, it doesn't just warm the air, it penetrates the structure itself. When the heat source disappears, the building doesn't immediately cool. It discharges that stored energy back into the space, gradually, over hours and days. Modern walls can't do this. A typical stick-built wall, drywall, fiberglass, vapor barrier, siding, weighs around 10 pounds per linear foot. It has almost no capacity to store heat. The moment the furnace stops, the warm air escapes through leaks and thermal bridges, and there's nothing in the structure to replace it. In medieval buildings, the walls are the battery. And the material mattered more than we usually admit. Scandinavian builders harvested trees that had grown slowly for 80 to 100 years in frozen soil. The growth rings were extremely tight, producing wood far denser than modern plantation timber. 1 cubic foot of old-growth pine weighs more than 37 pounds, nearly a third heavier than modern lumber. That density translated directly into thermal stability. Cold doesn't instantly pass through dense material. It moves slowly, like a tide pushing through thick stone. In a 12-inch log wall, it can take 12 to 18 hours for exterior cold to reach the interior surface. By then, the fire has been rebuilt. The cycle resets. This is not insulation, it's time delay, and time in cold climates is survival. But thermal mass alone isn't enough. Even the heaviest wall fails if air moves freely through it. This is where the second forgotten principle enters: airtightness. Despite modern membranes and flashing systems, most new homes leak air constantly. Blower door tests show that the average house leaks the equivalent of a permanently open window, roughly 20 inches by 20 inches in size. That's the enemy modern furnaces are fighting. Medieval log builders attacked this problem directly. Every log was scribed to fit the one below it exactly. The work was slow, painfully slow. A single room could take months to frame. But the result was a wall with virtually no airflow. Any remaining gaps were packed with sphagnum moss, harvested from bogs. When compressed and dried, the moss expanded into microscopic voids. Over that came a clay mixture reinforced with animal hair, a flexible, breathable seal that hardened without cracking. Moisture could escape. Air could not enter. When modern researchers test centuries-old log cabins today, many meet or exceed contemporary passive house airtightness standards, without plastic wraps, without chemical foams, without mechanical systems. A building made with axes and moss often seals better than one made with engineered composites. That fact alone should give us pause. If medieval builders had relied on open fireplaces, none of this would have worked. The image we carry of early cabins, flames roaring in an open hearth, smoke climbing a chimney, is deeply misleading. Open fires are not ancient efficiency. They are ancient waste. They pull enormous volumes of warm indoor air and eject it outside, creating negative pressure that drags cold air in through every crack. In extreme cold, an open fireplace can make a house colder than if no fire were burning at all. Scandinavian builders learned this lesson early, and instead of abandoning fire, they transformed it. Their solution wasn't to heat the air, it was to store heat in matter. Across Finland, Sweden, and Norway, a specific type of heater emerged: massive masonry stoves built from stone, brick, or soapstone. Known by various regional names, these heaters weighed several tons and dominated the center of the structure. They were not designed to burn constantly. Instead, the fire was brief, intense, fast, and clean. 1 or 2 burns per day. The goal wasn't flame, it was saturation. Inside the stove, hot gases didn't shoot straight up a chimney. They were forced through a maze of internal channels carved into the stone. Every turn stripped heat from the exhaust. By the time smoke exited, it was barely warm. That energy didn't disappear. It became stored time. The stone absorbed it. And for the next 12 to 18 hours, the stove slowly released that heat back into the living space as radiation. Not hot air, but warmth that traveled in straight lines, soaking into bodies, furniture, walls, and floors. This distinction matters more than modern systems acknowledge. Radiant heat doesn't need high air temperatures to feel comfortable. You can feel warm at 60 degrees if nearby surfaces are hot. Your skin absorbs infrared energy directly. Objects warm first. The air follows later. Forced air systems work backwards. They heat air quickly, then watch it rise, stratify, and escape. The sensation of warmth disappears the moment airflow stops. Masonry heaters remain warm long after the fire is gone. They don't chase heat, they release it on schedule. This wasn't theoretical, it was measured. In 2003, Finnish researchers reconstructed a traditional smoke-room cabin, an early heating design predating chimneys, and tested it under controlled winter conditions. Outside temperatures were -13 degrees Fahrenheit. The test was simple: light one fire, then do nothing. Using about 45 pounds of wood burned over 2 hours, the cabin stayed above 59 degrees Fahrenheit for more than 16 hours. No additional fuel, no airflow, no modern insulation. A modern oil-heated home would burn roughly 10 times that energy in the same window. This wasn't efficiency by modern metrics. It was efficiency by outcome. The goal wasn't maintaining a precise temperature. It was maintaining livability when systems failed. The heater was only part of the equation. The interiors themselves were designed to cooperate. Modern architecture favors open space, high ceilings, large volumes of air. Visually impressive, thermally disastrous. Warm air rises and pools where no one lives. Floors stay cold. Energy demand spikes. Scandinavian cabins rejected this entirely. Ceilings were low, often around 6.5 feet. Rooms were small and separated by doors. Heat stayed where people were. The central living and cooking space remained warmest. Sleeping rooms were cooler, intentionally. This wasn't discomfort, it was strategy. People slept under heavy wool, fur, and layered bedding. Lower nighttime temperatures improved rest and reduced fuel consumption. There was no reason to heat unused space to daytime comfort levels. This is thermal zoning in its purest form. Heat only what you occupy. Store heat where it matters. Let the rest remain dormant. Modern homes do the opposite. Entire volumes are heated continuously. Guest rooms are kept warm year-round. Ceilings trap heat above head height. Energy is spent maintaining air temperature instead of surface temperature. Ancient builders treated heat as a resource too valuable to waste on empty space. Then there was the ground. Modern slab-on-grade foundations are massive thermal bridges. Concrete conducts heat efficiently, straight into frozen soil. Once energy enters the ground, it is gone. Scandinavian cabins avoided this entirely. They were raised on stone piers, lifting the wooden structure above the earth. This created an insulating air gap beneath the floor. Floors themselves were thick, often double-layered planks with moss or sawdust packed between them. The goal was separation. Heat stayed in the building, cold stayed in the ground. Even when snow piled beneath the cabin, the structure remained thermally isolated. No slab sucking warmth downward, no continuous conductive path. Every component worked toward the same objective: delay heat loss long enough for life to continue without constant input. This system didn't emerge from theory, it emerged from failure. Structures that leaked air rotted, buildings that lost heat too fast were abandoned. Designs that required constant fuel collapsed when supply ran out. Over centuries, Only what worked remained. That evolutionary pressure shaped a building philosophy centered on resilience, not convenience. And that philosophy is almost entirely absent from modern codes. We measure peak efficiency. They measured survival time. We optimize for steady-state conditions. They optimized for worst-case scenarios. That difference explains why a medieval cabin can outlast a blackout, and a modern house cannot. The old ways didn't disappear because they failed. They disappeared because we no longer needed them. Or at least, we thought we didn't. After the Second World War, Europe and North America faced an unprecedented demand for housing. Entire cities had been damaged. Millions of families needed shelter, fast. Speed became the priority. Standardization followed. Labor had to be minimized. Materials had to be cheap, light, and easy to assemble. Hand-scribing logs took months. Stick framing took weeks. Solid timber walls required patience. Thin walls filled with insulation required factories. At the same time, something else changed everything. Energy became cheap. Oil, gas, and electricity flooded the market. Heating no longer needed to be efficient. It only needed to be available. If heat leaked out, you burned more fuel. If rooms were oversized, you raised the thermostat. If the building cooled quickly, it didn't matter. The furnace would catch up. The house became a machine permanently plugged into the grid. Resilience stopped being a design goal. Instead of asking how long a building could stay warm on its own, we asked how cheaply it could be built up front. Building codes followed that logic. They optimized for insulation values, air exchange rates, and equipment performance, all under the assumption that energy would always be there. But systems designed around infinite supply fail the moment supply becomes uncertain. And that moment has arrived. Energy is no longer cheap. Grids are stressed. Weather patterns are more extreme. Blackouts last longer. Heating costs rise faster than wages. Suddenly, people are discovering that their homes, expensive, modern, compliant, are fragile. Cut the power, and comfort disappears in hours. That realization has sparked a quiet reversal. Not everywhere, not loudly, but steadily. In Germany, Austria, and Switzerland, architects and engineers have begun returning to principles that predate central heating. Solid wood construction, mass timber, is no longer experimental. Cross-laminated timber panels now form walls thick enough to store heat, not just resist it. Masonry heaters are reappearing, not as rustic novelties, but as primary heat sources. Floor plans are becoming more compact, ceilings lower, spaces zoned. Buildings designed to slow heat loss instead of endlessly replacing it. This isn't nostalgia. It's physics reasserting itself. The data supports it. A long-term study conducted in 2018 by the University of Innsbruck compared solid wood houses to conventional builds over 5 years. The results were consistent. In winter, the wood homes used roughly 40% less heating energy. In summer, many required no air conditioning at all. The thermal mass buffered heat swings in both directions. Residents reported fewer drafts, more stable temperatures, and better air quality. Wood naturally regulates humidity, absorbing moisture when levels rise and releasing it when air dries out. No mechanical systems needed, no active control. The buildings handled it themselves. Durability told an even starker story. Modern houses begin degrading almost immediately. Vapor barriers tear. Fiberglass settles. Water infiltrates assemblies that cannot dry. After 30 years, major repairs are expected. Log buildings behave differently. As solid wood structures settle, joints tighten, cracks close. A 50-year-old log home is often more airtight than when it was new. Some of the oldest Scandinavian cabins have stood for 6 centuries, not because they were overbuilt, but because they were built correctly for their environment. One type of building depreciates the moment it's finished. The other improves with time. None of this means we need to live like medieval farmers. The lesson isn't to abandon modern materials, it's to abandon modern assumptions. Thermal mass still works. Airtightness still matters. radiant heat still outperforms forced air. Physics hasn't changed. If you're building or renovating today, these principles can still be applied. Solid wood walls or mass timber panels provide storage, not just resistance. Stone elements, masonry heaters, heavy hearths, interior walls act as thermal batteries. Airtight construction prevents energy from leaking away. Compact layouts keep heat where people actually live. And most importantly, design should consider failure. A resilient house is not one that performs well when everything works. It's one that remains livable when systems stop. That's the metric medieval builders optimized for. The Scandinavian farmer in his 14th century cabin was not primitive. He was a practitioner of applied physics. He understood that heat is easier to store than to replace. That air movement, not cold, is the real enemy. That radiant warmth feels better at lower temperatures. And that working with natural forces is always cheaper than fighting them. We traded that wisdom for speed and cheap fuel. Now, as energy becomes expensive again and climate grows less predictable, the bill has come due. The knowledge was never lost. It was buried under convenience. Every time a building is designed with mass instead of emptiness, airtightness instead of leakage, and stored heat instead of constant consumption, that wisdom resurfaces. Not as history, as survival engineering, and it still works.